What about this one, sir?
Now it's showing.
Fine. Yeah, good afternoon, guys. Yeah, in this session, what we are going to do now, in the last session, we have discussed about the naive-Bayes classifier, as well as we have discussed about the problem based on the naive-Bayes classifier, right? And that we are discussed about the types of the naive-Bayes classifier and how to approach the naive-Bayes classifier for the classification. And we have discussed that in that naive-Bayes classifier, we are not having a much parameter to tune the classifier. So we can say that naive-Bayes classifier it is a non-parametric one. But in the case of text classification, we are added a one parameter. It's called the lambda parameter. That is to avoid the zero frequency operation. That is also we call it as a Laplace smoothing. Fine. So in this session, what I am trying to do now. So first, I try to explain the dimensionality reduction using a PCA, and we will discuss the drawback of PCA. Then I will give the idea about a linear discriminant analysis, right? So why the linear discriminant analysis is evolved, right? So we are going to discuss that particular concepts. After that, I will show you by using a naive-Bayes classifier how to approach the text classification. Okay, so I prepared a one PPT. I will show you all the in that particular PPT. I am considering the problem based on the text data, right? If I show that one, you can easily understood how to approach the applications, right? So then what I am going to do now, I am going to explain the dimensionality reduction first, and then we are move on to the naive-Bayes. After we are completed that, we will see the implementation of naive-Bayes for the text classification as well as the PCA implementation, right? We will see a principal component analysis. So initially we need to know what is the need for principal component analysis. What is it? Why exactly this principal component analysis is evolved in case of the machine learning applications. Okay, this also we say it is a curse of dimensionality, or we can also say it's a dimensionality reduction. Okay, so in the morning session we are shown one block diagram, right? So any to given regarding the ML algorithm. So I try to start with that particular block diagram because it is a more suitable and it's a more informative while we are discussing about the ML algorithm, right? So in that block diagram, we are started with the data warehouse. All the ML applications, the classifier or regression applications, it always starts with the data warehouse. So naturally, whatever the raw data it's available, it is not at all it is suited for our ML algorithm, right? We are doing some pre-processing techniques, some feature engineering is we are doing in that particular raw data, and we are trying to extract the potential features in order to get the better performance from the model, right? That is actually more common for any type of classifier, right? So we have to understand why this dimensionality reduction plays a vital role. Okay, simply we can say is, if we are going to do a human disease diagnosis, let us consider the medical application, because I am much interested to do a medical applications. Okay, fine. So in that medical application, we are going to diagnose the cancers, right? So cancers and the non-cancers patient. Okay, so during that cases, so based on the CT images, we have to concern with the so many features for this kind of classification. Okay, so if you take that many number of features, if you train any model, the model become very bulky. Okay, the manipulation, it's also it takes a huge time to converge, and moreover if you give such a huge features, right, that also create a problem while we are making a ML model, Okay, so in while we are doing ML model, the two things is we have to concern, guys. So we have to design a model with a low bias and low variance, right? We try to understand this terminology while we are doing a ML model designing, right? So in that case, what I need to do, I try to capture the potential features out of the maximum available features. I try to capture the potential features. So what to do in that particular feature? See, you have to clean the features which is extracted from the data, and then we have to utilize for our ML model. Okay, how to do the cleaning process? So in that cleaning process, we may reduce the redundant feature, or otherwise we can also choose the potential features. The potential feature, it means that it has a more variance, or it has a more information. In other words, we can say, right, that is, we called it as a potential features, which means the feature, it's quite enough to discriminate the classes. Okay, such a feature is, we say it as a potential features, right? So how to identify such a features from the available data, from the available features? That is the one question. The another one more thing is, so how to reduce the dimensionality? What is exactly the dimensionality reduction algorithm does? Okay, what is the need of a need for the PCA? Okay, let us see the picture which is illustrated in the figure one. Okay, see here I am having a two pictures. I illustrated two pictures, sorry, three pictures, right? So one is for one dimensional picture, and two is actually a plane two-dimensional one, and third one is a three-dimensional cube, right? So consider the scenario, I am going to drop a coin in that particular line. So what about the traveling time of the coin, and moreover your accessibility of the coin? It is very easy, right? We can easily see the coin where it is exactly traveling, and we can do all the necessary things, and also we guaranteed that the coin definitely meets the destination part, right? Whereas in case of a two-dimensional, if you look at that one, it takes a more way, the more sorry, it takes a more path, or it takes a very difficult the way to reach your destination part. Am I right? Look at that. If you are drop a coin in the particular right hand, so it is difficult for you to identify the coin, and moreover it is difficult to, it is not guaranteed to reach you, right? That is also, if even in the two-dimensional itself it looks like that, if you see the third dimensional, it is more difficult to reach. So what it infers, this picture infers, if your data is actually the dimension is lesser one, it is guaranteed to get the proper output. That means it is not a proper output, we can say is, it is easy for to access, right? It reduces the manipulation, moreover, right? It reduces the model complexities, right? So the complex manipulation things. Okay, so for what we are going to do now, this is the reason why PCA evolves. So this is a need for PCA. So the high dimensionality data is extremely complex to process due to the inconsistency in the features, which increases the computation time and makes a data to process in potential way, and we have to do some EDA more convoluted the data. Okay, so it is actually the exploratory data analysis. We have to do the data analysis for that particular data, if suppose it is a too bulky, right? So this is the reason why PCA comes into the picture. So the PCA, it's a we are abbreviated it as a principle, that the abbreviation of the PCA, it's a principal component analysis. It identifies the principal or potential component from the particular data, which help us to give the proper classification efficiency, and moreover it reduces the cost of computation, right? Let us see the original data. It looks here, it is illustrated in this figure one. All right, so here we are having a more number of columns. What does it mean, the columns? So in the morning itself I told most of the feature is actually in the data frame. We are arranged as a column. Each column indicates the number of feature which is used in your classification application, right? So original data is we are considering how what to process in your original data. We have to do with three process to reduce the dimensionality reduction. How we are reducing the dimensionality reduction? We can also do a some forward pass operation, some backward pass operation, filter operation, as well as the wrapper operation. So many things we can do a feature selection or feature reduction process, right? So what are all the things we have to concern while we are doing a reduction? Okay, that is we are going to see. So three things is we have to keep it in our mind. One is removing the inconsistent one, because that feature is not quite enough to fight with the problem, and it will not helps to improve your model performance. Okay, such a feature is we can say is it is a remove inconsistent one. So we are trying to remove that inconsistent one. Fine. So to remove the inconsistent one, first we have to identify which is actually inconsistent, right? So far that is we have to identify. The second one is a redundant data. So for example, if I am having a 10 features in my data, right? Considering a 10 features, if the first features and the fourth feature is highly correlated, which means it has a 90% of correlation, what we have to do, we have to suppress any one of the data, because both are almost near, right? So the same information only, it's actually given by the two features. So what we have to do, that is actually going to act as a redundant data. So far we have to filter out that. The next one is what we have to do, highly correlated features. So redundant, highly correlated. So two thing is actually guys, redundant means it is not actually improving the performance of the model, whereas a highly correlated is also a kind of redundant, but the condition is both the feature are actually correlated. Fine, one of the feature is we have to suppress, right? This is actually the interlinked one guys, the redundant data and your highly correlated. Okay, fine. So this is the three things we have to do it in your original data set. So from that we can attain the new data space with the lesser feature that retains most of the informations. What kind of information is required for your application? It may be a face detection, it may be a face recognition, whatever it is, right? So far, for this process, we have to know in this slide what is exactly the PCA. What is the definition of the PCA? So the PCA, the principal component analysis, is a dimensionality reduction technique that enable you to identify the correlation and patterns in a data set, so that it can be transformed into the data set of significantly potential one with the lower dimension. Especially it ensures that without losing any important features. That is very very important guys. That is actually the key factor of a PCA, right? This is how the PCA works in our data. So we will see the step-by-step process what we have to do in a PCA. So first, if you take a data, consider it's a the data is actually in the form of a plane, right? It's a two-dimensional representation, or otherwise we considering the features, the 10 features for your application, for your face recognition application, right? So what we have to do, first step is we have to standardization of the data. So what is the standardization of the data guys? What is the standardization? Either we try to make the data in the same scale. Okay, so if you are having a different features, so with the different, maybe with the different scale, you try to make it as a, we will try to standardize the data, right? After that what we have to do, after we are standardize the data, we have to compute the covariance matrix of the particular data, right? So covariance matrix, what about, what is exactly the covariance matrix it does? We try to identify the relationship between the existing features. That is actually the role of covariance, right? So what then, what about the correlation? So correlation is also, it actually try to identify the relation, but the key point here is correlation, it tells about the direction as well as the magnitude, in which direction the data is attached highly, as well as, and what is the magnitude of the attaching. For example, if the value is negative, so it is negatively correlated. Okay, if the value is actually 2.3, so 2.3 times it's negatively correlated, like that, right? So most of the time it's not a 2.3, guys, consider it's a zero point 0.3, right? Why? Because the correlation, it's always the value is fall between a -1 to +1, whereas in the covariance it tells about the direction, but it not tells about the magnitude value. That is a key difference between your correlation and the coefficient. And moreover, your correlation, it's a kind of, it's a function of covariance, right? We are takes the covariance, and the ratio, we have to calculate the ratio between a covariance to standard deviation. That is, we defined it as the correlation of the data, right? So far in this application, we try to compute the covariance matrix, right? Then what you have to do, you have to calculate the eigenvector and eigenvalue of the covariance matrix. See guys, if you people are interested in this application, what you have to do, simply takes the standardized data, then you apply the eigenvalue, eigenvector, you just simply skip this covariance steps. Okay, look at the result. So what is the impact of covariance, you can easily realize it. Okay, without doing this process, this will not give a very good result, guys. Okay, this step is a very important while we are doing a dimensionality reduction, right? So next, what you have to do, you have to compute the principal component from the eigenvalue, eigenvector. What you have to do, we have to identify the potential vectors. For example, if you are having a 10 data, just a minute guys. Yeah, if you are having a 10 data, if you take the eigenvalue and the eigenvector of that particular data, what happen, that means 10 features, you get a 10 eigenvalue, am I right? If it is a 10 features with the sample value is 10, so it means 10 cross 10. So if you apply a eigenvalue, you get a 10 eigenvalues, right? So far, what does it mean? You are having a 10 eigenvalue. Out of that, which is having a highest value, that particular value, that particular position vector, or we can say that particular value, by using that value, if you compute a vector, that is we called as a potential one, guys. Okay, that means whatever the transforms we are applied on the data, that vector is not changed, right? That is actually the potential vector. Okay, by using that, we can, that is we called it as a principal component. Okay, so based on that principal component, we are trying to, we are trying to reduce the dimensionality reductions. We will see how this dimensionality reduction data is done. Okay, the last step is a very key step. It's used to reducing the dimensionality of the data. Okay, after we are computed the principal component, this is how the flow of the dimensionality reductions techniques. So let us consider the problem once again. What is we have to do? So look at here, guys. This is how the standardization we have to do, right? So suppose if you're having a data, the two columns. Okay, so this is having a one scale and this is having another scale. If you are having a two different scales, okay, it is difficult you to take a decision, and moreover it affects your problem, right? Sorry, it affects your model, it creates a problem, right? So far we have to do a standardization. What is the general form of a standardization? The particular variable value minus mean value of the column, okay, divided by standard deviation of the same column. Okay, if you do that, we are trying to makes the data with the same intervals. Okay, so standardization is all about scaling your data in such a way that all the variables and their variables are lies within a similar range. Okay, so next step, what we have to do, the next step we have to compute the covariance matrix. So what are all the things it exhibits by the covariance matrix? Let us see one by one how co-dependent of the two variables are. If you are having a 10 features, if you takes the in this case actually, so I try to interpret with this matrix itself. Here we are having a 2 cross 2 matrix, right? Which means we are having a two observation samples. One is a and another one is B. We are trying to measure the covariance. The first element indicates we are trying to measure the covariance between A comma A. This is measure a covariance between A comma B. This is B comma A. These both are actually equal, guys, because a comma b and the b comma a, it's actually commutative. So these both are equal actually while we are computing the covariance, and moreover this one is a covariance of b comma b. Okay, the secondary data itself, it calculates the covariance. So what it exhibits, how the codependent of the two variables are, and it exhibits the so what kind of relationship it actually illustrates. It illustrates either a negative covariance. So what is a negative covariance? It is indirectly proportional. The both the features are indirectly proportional. So it means both are variance one. Okay, and also if it is a positive covariance one, what happened? The directly proportional one. So either one of the data you have to suppress. That is, we can say it as a redundant data, right? So in the step 2, compute the covariance matrix. A covariance matrix expresses the correlation between the different variables in the data set. It is essential to identify heavily depends on the variable because they contain biased and redundant information, which reduce the overall performance of the model, right? The next step. So what is the third step? What we have to do after we are computing the covariance matrix? We have to calculate the eigenvalue and the eigenvector of the covariance matrix. In the morning itself, we have discussed about the eigenvalue. In that place, actually, I try to explain. So which out of all the distributed value, which is actually the eigenvalue or eigenvector? Eigenvalue, it shows that it is a potential features. It doesn't change the direction if you apply a transform, any kind of transform in your data, right? This is how, because it is, you can't ignore that particular feature, because that feature is a potential enough to represent the data, right? So that is, we say it is a eigenvalue one, eigenvectors, right? So simply we can say the principal components. So first, mathematically, we try to explain about the eigenvalue and eigenvector. Then I try to explain about the principal components, right? So the eigenvalue and the eigenvectors are mathematical constructs that must computed from the covariance matrix in order to determine the principal component of the data. So then the question arises, what is a principal component? So we have to define the principal components are the new set of variables that are obtained from the initial set of variables, right? So we are applied some transforms that brings the new variable from the original original or initial variables, right? So they compresses and possesses most of the useful information that was scattered among the initial variables, right? This is how we can say it is a principal components. Okay, so before after going to before going to see the in a depth into that particular process, first we have to describe the definition of the eigenvalue and eigenvector. So what is exactly the eigenvalue? It simply denotes the scalar of the respective eigenvector. Okay, in the morning itself I told, right? It's a kind of magnitude. It's a kind of, we can say, if it is R vector, the R value which actually we can say it is an eigenvalue. Okay, whereas the eigenvector are those vectors when a linear transform is performed on them, then the direction doesn't change. That is a, we can say that vector is, we can say it is an eigenvector. So that vector has a more feature, guys, so which is used to classify or predict the, so to perform the prediction applications. So look at here, what is the fourth step? You have to compute the principal component. So here principal component comes into the picture, right? So once we have computed the eigenvalue, eigenvector, all we have to do all we have to do is order them in the descending order. Just now I said, right, the highest eigenvalue which indicates that particular feature is a high potential one. So far, we, after we calculated the eigenvalue, what we have to do, we have to sort the eigenvalue. Okay, so while you are sorting like that, what happened? You are bringing out the significant data which is present in your eigenvalue, right? So far, so where the eigenvector with the highest value is the most significant, and thus forms the first principal component. Okay, look at this particular picture, guys. This picture explain about the principal component. So the PC1 is the most significant and stores the maximum possible information within that, right? That is we call it as principal component, right? The second principal component, what happened? It try to, this second principal component also having a significant information, but it is lesser than your first one. So in such a way, we have to arrange the eigen value of the particular data, right? So this is the graph. It indicates the principal component 1 and principal component 2. The direction of the most variant is actually covered with the principal component 1, and the second most variance is actually covered with the principal component 2. So at last, what is actually the ultimate? Our ultimate is trying to reduce the dimension of the data set. For example, in this data set, look at this particular data set, guys. How many data is available right now? Right, it is available in the form of 4 features, whereas in this previous process, in this original stage, look at here how many features are presented. 1 2 3 4 features are presented. After you are transformed this particular, sorry, not 4, it's a 8 features. After we are performed the dimensionality reduction, it produced the 3 feature, which is enough to classify or discriminate the, it try to discriminate the people or data, whatever it is, right? So what is the fifth step? How we are reducing the dimensionality? Reducing the dimensionality of the data, the last step is performed in the PCA to arrange the original data with the principal components, right, which represents the maximum and most significant information of the data. Okay, so this is the reason why they are not exposed to the universal uniform, right? So look at here. So the last step, just now we are described, right? So the last step is performed the PCA to rearrange the original data with the final principal component, which represent the maximum and the most significant information of the data. So next step, what we have to do, the data set. So here we have to perform the PCA in Python. So step-by-step process is actually waiting for you guys, right? So here we have to, the data set is described based on the movie rating. Okay, the data set and contains the rating from the 700 plus users for approximately. So what is our plan or what is our idea? So the problem statement to perform the step-by-step principal component analysis on movie review data set on order to in order to reduce the dimensionality of the data, right? So I try to solve the problem. Okay, so when should I use the PCA? That is the first question while you are applying a PCA. Do you want to reduce the number of variable but are not able to identify the variable to completely remove from the consideration? During that time, you have to use a PCA to identify the potential features, guys. Okay. And second part, do you want to ensure your variables are independent each others? So what PCA concerns? What are all the features available in your data set? So each and every feature is a independent each other. It concern like that, right? Third step, what we have to do. So are you comfortable making your independent variable less interpretable? Which means whenever if we are reducing the dimensionality of the independent variable, if it affects the performance, what we have to do, we have to slightly add or improve the data, or otherwise we simply ignore it, right? Let us see how the principal component analysis works. Okay, look at this particular original data, guys. Okay, so here we are having a 2 vectors. Okay, there is a vector 1 and this is a vector 2. So what happened if you applied some transform on this particular data, right? If you applied a transform on this particular data, what happened? The same vector, it is presented over here, right? So the presented over here, this is actually the output of the PCA. So what exactly the PCA does, it takes your data projected on the eigenspace. That is the role of PCA. It takes your data from the original XY coordinates, which is scattered in our XY coordinates. Okay, try to project in the different subspace. That is, we say it is a eigenspace. Also, we can call it as a eigenspace. So in that space, it try to retains the most powerful information which is used to discriminate. So this is a actual step what we are discussed. So just before going to discuss the we are actually discussed more technical part about the PCA. Now we are just let's dive into the mathematics. Consider the features x1 and x2. So what is our first step? This is actually the scattered value. Okay, this is a data which is scattered here. Okay, and then what we have to do, we have to calculate the x1 and x2 value. Okay, so here this is actually the centered mean vector for the particular scattered data. Okay, and this is actually the that particular center vector value 1.81 comma 1.91, because it is a two-dimensional data. So after that, what we have to do, what is our first step? We have to adjust the data. That is most important, guys. We have to standardize it. Okay, for that I try to take the two vectors and calculate the new features. It's called x1 is equal to the old value minus mean of the new value. Okay, likewise we have to compute it. Okay, x bar is nothing but your mean value. Okay, guys, so this is actually a we are extracted the or we are removed the mean of the original data. Okay, after we have performed that, we try to plot it in the x and y plot. So this is actual data adjusted data vector, data input vector, right? We are having a two columns, so we can say it is a two features with the 10 rows. Okay, 10 samples with the two columns. So what is our second step? This is how you have to create the data set, guys. So this is the data after completed the standardization. Okay, one thing you have to keep it in your mind, while you are doing a data adjusted data, the data will have a zero mean, which means we are shifted the data. We are trying to make the data with the zero mean. What is our second step? We have to calculate the covariance of the particular data, right? What is the formula for the covariance? So x minus x bar into the that means in that particular data we are having a two data, right? So first data is concerned about the first component, and second data it's concerned about the second component. For example, x1 and x2, right? So in such a way we have to compute the covariance matrix of the particular data. So x minus x bar, it's actually the mean of the first column. This is actually mean of the second column, guys. Okay, so what we have to do after we are computed the eigenvalue eigenvector, you have to calculate the after we are computed the covariance matrix, we have to calculate the eigenvalue as well as the eigenvector, right, for the particular covariance matrix, right? So this is actually the covariance matrix. After we are apply the eigenvalue eigenvector, this is how we got the eigenvalue and the eigenvectors. Okay. I hope you understand this particular problem. Okay, it's very simple, guys. Because in the school days onwards, we know how to calculate the eigenvalue and eigenvectors. Okay, this is the actual covariance matrix of the particular given data. Okay. Okay. This is a summary of the particular data, guys. Okay, so in that 2 cross 2 matrix, we have a two eigenvalues. One is a 1.28 and another one is a 0.049. Look at here. After you are computed the eigenvalue and the eigenvector, that means you takes the covariance value, try to identify the eigenvalue A minus lambda into I, where I is a identity matrix. Okay, after we performed all the process, we attained the 6.6166 lambda, 0.6154, 0.6154, 0.7166 minus lambda. So this is how I said, guys, covariance of A comma B or B comma A both are similar. Okay, so next what you have to do, you have to identify the determinant of the particular matrices. Okay, look at here, guys, each and every step is we are using here. We are doing some addition operation, some multiplication operation, and then we are calculating the determinant. All those things are we are discussed in the morning session, right? Okay, so after you are calculated the gradient, after we calculated the gradient value, sorry, after we calculated the a lambda 1 and a lambda 2. So this is actually a lambda 1 is equal to 1.28, whereas this is a lambda 2, it's a 0.04, 0492. What does it mean, guys? So first eigenvalue and the first vector is a potential one. Out of the two values, so first one the potential one. Okay. So for first case, what you have to do, after finding the eigenvalue, you have to calculate the vector. Okay. So substitute this vectors, sorry, this value in the previous equation, we try to calculate the vectors. Okay, this is how the calculated vector, the two vectors. Okay, after we are calculated the lambda 1 and lambda 2, we simply substitute the lambda 1, guys. This is the lambda 1 substitution. Okay, this is actual value of the cases. This is actual value after we are finding that. Okay, so in such a case, this is actually the x1 and x2 value. After we are solving this one, we get the x1 and x2 value. So far the total summary of this particular problem, the eigenvector is given it as a 0.63673 and second one is the 0.735. Whereas similarly the same procedure, this is a final value after we are calculated the eigenvalue, that is 1.28. The similar same steps you have to follow it for the lambda 2. What is the lambda 2 value? It's a 0.0492. Okay, so this is another vector we attained. So to getting the value of both the eigenvalue eigenvectors of the data, we will see that. So this is the x1 and x2 variable for the eigenvector. This is the first eigenvector and this is the second eigenvector, the corresponding eigenvalues 1.28 and this is the eigenvector, whereas the lambda 1 is the 0.49. This is the potential eigenvector 2, right? So we need to know how much of the variance it has, because already in the morning itself I told, guys, while you are doing a data analysis, which data, which component is having a more variance, that is actually the informative data. Okay, morning one of the person is asked how to identify the eigenvalues. Actually eigenvalues is it is pretty simple to identify. Okay guys, okay guys, so what you have to do, you have to extract the features from the particular data. If you are considering the psi image, you have to extract the potential features from the particular data. After that you have to apply the eigenvalue or eigenvalue approaches like a PCA approach to reduce the dimensionality of the data. Okay, let us see here what it does. So the total variance of the particular data, we can say is it's a ratio of the two eigenvalue. So what is the ratio of the two eigenvalue? It's a lambda 1 by lambda 2. This is actually, we says it as a lambda 2 by lambda 1. So the first vector itself having a more potential, it has the 96% of variance. So only one data is enough to represent your whole data. Okay, so instead of two vectors, is it more than enough to represent with the one vectors? Okay, this ratio, it indicates the variance of your particular data. Okay, and this is we called it as a principal component 1. So what is the second stage? This is our second stage. This is we called it as a principal component 2. Okay, so this is how the lambda 1, this is a vector, the first vector, and this is a second vector. So in the previous slides, I am not explained much about this. Am I right? Look at here, guys. So in the eigenvector 1, it moves the right direction, and 0.3725, it actually directed or up. Okay, so the vector 1 is 0.678, 0.735. This is actually 0.678, 0.735, somewhere around, it's somewhere around present here. Okay, right? Then what happened? So the next one is actually it actually moves downwards. So this is actually the downwards. So look at the distribution of the data. In this direction, the data is almost all the data is distributed. Okay, only some of the data is actually deviated from this position, guys. Look at here, maybe at this second data. The second data alone, it actually elevated from the line or from the direction. Otherwise, all the data is actually in the same direction. This is we called it as a principal component analysis 1. Okay, I hope so you people are much clear about a PCA, how it is actually applied in the data. Okay, so the total variance of the given data, if you want to identify the total variance of the given data, it's simply you have to add the eigenvalues. If you add eigenvalues, it gives how much of variance which is present in your data. In the morning itself, I told whenever you want to do any classification or regression application, you need to have a highly variance data. Then only we can easily split the particular data. So by this process, we are able to find extra exact line that characterize the data. The first eigenvector will go through the middle of the data point as if its line is the best fit, right? This line, it's a best fit. The second eigenvector will give us other lesser important patterns in the data. That is all the data point follows the main line. So after you are identifying the eigenvalue, eigenvector, then what you have to do, we have to sort the value, okay, which is having a more potential. That value is you have to keep it in the top, and less potential is you have to keep it in the bottom. Likewise, you have to give the ranking of the eigenvalues. Okay, if suppose if you are having a more than 10 features, you may get the 10 eigenvalues, so you have to prioritize that. Okay, so in out of this, what I'm going to do, what is my application? I try to reduce the dimensionality, right? So here the dimension of the data is 2. I'm trying to reduce it as a 1. So far I'm considering only the one potential eigenvectors. Okay, 0.678, 0.739. Guys, I hope so until this you people are very clear what is exactly PCA. Am I right? Any doubt regarding this? Until this, any doubt? Step 4. Sorry guys, some problem with my, okay, fine. I hope so. Shall we move on to that? Okay. Okay. So what I'm going to do now, after I am taking the potential vectors, so that is actually the key factor what we are going to do now. We will see. So this is our original data, guys. So the fifth step is we are try to identify the new space. That means we are try to identify the transformed data, right? So what I am going to do after we are identifying the eigenvectors, so okay, right now you don't consider about the reduction. First you transform the data and then we are going to reduce it, right? So first what you have to do, you have to rearrange, guys. If suppose this value is actually second and this value is first, what you have to do, you have to reschedule it. That means you have to rearrange it. Okay, you have to arrange it in the descending orders. Okay, the eigenvalues is you have to arrange in the descending order. The same way you have to arrange the vector also in the descending order, right? So this vector arrangement is follows your eigenvalues. Okay, for example, I am telling 10 features, you are having a 10th eigenvalue is a highest eigenvalue. So what you have to do, that value should be, you have to place in the top. Okay, after that you try to keep all the eigenvalues the similar way. So first eigenvalue corresponding vector is you have to place in the first position of the vectors. Okay, you have to arrange the vectors in such a way as similar to your eigenvalues. Okay, based on the eigenvalue only you have to arrange the eigenvectors. That is, you keep it in your mind, right? So what I am going to do now, after I am calculated the eigenvector, I try to multiply the data. So what happened while you are multiplying like this, the data is actually the data is transformed into the new subspace, that is we called it as a eigen subspace. Okay, so far I try to give it as so y1 and it goes on. This is actually my new data. This is my new data, right? New transformed data. Okay, so I want to reduce the dimension of the data. What you have to do, guys, this is actually the new data with the two components. Two component. Here we are having a two principal components, right? Top two principal components, because the data itself it is two. That's why we are having a two. So next what you have to do, already we know that the first data itself, it has a more potential enough to express about the data. So what I am going to do now, this is a tricky step, guys. You have to eliminate such a vectors. If you are having a 10 vectors, you are going to reduce the dimension by 5. The last from the bottom to top, you have to reduce the vectors. That is very, very important. Okay, so here we are having a 2 vectors, we try to reduce the second column and then you have to transform it. This is, we call it as a dimensionality reduction operation, guys. This is how we are reduce it. So initially, why having a 2 dimension? Look at here, after we are transformed, it has the only 1 dimension. So this is the representation of the 1D vector along with the first principal component. I hope so everybody is clear with this principal component applications, right? So what is the advantages and disadvantages of the dimensionality reduction, we will see. So from the starting point itself, guys, we completely understand why this is required. And then we understood that the eigenvalue eigenvector, it try to take the potential features which is presented in your distributed data. Okay, and then what we are done, we are trying to reduce the dimensionality of the features by using the principal components, right? So now we are going to see the advantage and disadvantage of the principal component. So the advantages, it removes the correlated features because it takes the eigenvalues. Based on the eigenvalue only we are choosing the features, right? Already I told in which feature having a highest eigenvalue, whenever the feature having a high variance, then only it has the high eigenvalues. Okay, so in such a way we can easily reduce the correlation of the features. The next what we have to do, we have to improve the algorithm performance. Once if they are reduced the data, or otherwise we can also say that if we are having a potential data, it's a much enough to express the operation, or it much enough to express the that means it is a deserve to do the application. It obviously improves your algorithm performance. Okay, and moreover it's obviously used to speed up the process. That is key point of while we are using a PCA. The very, very important thing is it reduces the overfitting, guys. In the morning itself I told you know what you have to do, you have to maintain the bias and variance. Okay, then only your model is, your model should be a optimum. The optimum model or the good model, we says that it's a zero bias and zero variance, right? So because reducing the dimensionality, once if you touch the data set or you are scaling the data set, what happened? Obviously it reduces the overfitting process. Okay, and moreover we can say it improves the visualization. Okay, that is a key factor, guys. So from the transformed data and your original data, if you look at, it looks a key factor. Okay, the representation, it means a lot. So the last, the disadvantage of this particular PCA is it's actually concerned all the features are independent each other. In some of the applications, it may have some interrelationship between the data. If you are performing the multi-class classification, let us consider. Okay, in that cases, in some of the class, it may have a same relationship. It may have some relationship between two vectors. Okay, two features we can say. Okay, fine. But PCA assumes that each and every features, the available features and all, it is actually independent each others. That is actually the biggest drawback of PCA. So what happened while you are transforming such a kind of data, the two class data getting overlap. Okay, this is actually pave the way. This actually paved the way to introduce the linear discriminant analysis. So linear discriminant analysis, what happened? It also concerned while you are projecting into the other space, the different subspace. Okay, even if we are projecting the data, it maintains the distance between the two different classes. That's why it called linear discriminant. It actually discriminates the data in the linear way. Okay, the projected data is discriminants. And the another one more disadvantage of the PCA is actually you have to do a standardization each and every time while you are applying any PCA operation on your data. That is must. So the third important drawback is while you are transforming a data like that, some little bit losses happen or some of the information is missed while you are transforming from the one subspace to another subspace. This is how the PCA works. This is a complete scenario of PCA, right? This is how we are reducing the dimensionality reduction, guys. I hope so you people are clearly understand the operation of the problems. Guys, any doubt? Guys, any doubt? Fine. Yeah, surely I will share all the PPTs and as well as the uh, IPYNB files and all, guys. Kindly go through all the IPYNB file, guys. We are actually arranged all the files in the self-explanatory way, right? So you just make use of that. Is it very easy? And most some of the codes actually we are trying to implement it from the scratch. Okay, kindly go through such a code and all. Then only you can really understand what is really happening, how we are mapping into our real-time implementation. Okay, that is very important. Ultimately, that is what I am expecting. Okay, so next what we are going to do now, in the morning session actually some of the people are asked kindly share the information regarding text classification. I will show that. After that we try to implement the codes. Let's strictly move on to the code part. Okay. Just a minute, guys. Okay. I hope so. The screen is visible, right? Guys, screen is visible? My screen is visible? I hope so. My screen is visible, guys. PPT is visible?
So yes, so it's visible.
Yeah, fine. So what we have to do, so this is actually, I try to, actually this is the PPT, original PPT I prepared for the naive-based classifier for the text classification. Okay, so just I give a quick recap about this particular application. Okay, how we are utilizing the naive base for the different application. So the spam application is already we are discussed. Okay, I will show you the important part, guys. So these are all the actual different application. This is a spam and non-spam application, and this is in the originally they are identified who is actually wrote this particular paper. Okay, they are classified this particular journal informations by using a Bayesian method, and this is a male or female authors. So based on the data, based on the journal data and the magazine data, it identifies whether the author is a male or female. It's a classification one. And this is actually the positive or a negative movie review, guys. This is the movie review, and especially the recommendation systems, all the NLP process, they are concerned only the base classifiers. Why? Because the base classifiers works, it's a kind of a non-parametric one, and moreover it gives a more accuracy, because in that case we are having a huge data, so we can represent the four important metric in such a way it's easy for us to exhibits the exact results or exact class of the particular data, right? We will see that. So this is a more apt one for the text classification, guys. Any text classification you want to do, you just kindly go with the naive based classification. Okay, fine. So look at here, the positive negative movies, how to they are classifying is, especially look at this particular data. It's an unbelievable disappointment. Okay, so disappointment is a key feature. We have to choose, and this word is a key feature for negative review. Okay, so look at here, this one is actually um, so great is actually the keyword, as well as richly applied star. Okay, the richly is actually the another keyword for the positive review. We concern like that. Look at here, here also great. So somehow we can say it is also positive review. Okay, so likewise you have to split the feature. You have to extract a feature from the data. Okay, based on that features you have to apply the basic classifiers. Okay, this is how you have to extract the features from the particular data. I hope so you understand how we are extracting the features for the text classification. So this is actually the another one more application. It's simply like, so based on the article, this is a major very highly demanding application, guys. And nowadays, you know, most of the journals or review systems and all, they are trying to implement this particular article identification system It's used to categorize the available articles, whether it comes under the chemistry, whether it comes under drug therapy. It based on the bag of words in which is presented in the articles, right? So this is actually the text classification. So the spam, non-spam, language identification, sentiment analysis, authorship identification, and assigning a subject categories, topics, or genders. So all these areas, this text classification, name-based classifier works. So how this one is works? What we have to do exactly? You have to take a document. You know, that is actually considered as a D. Okay, so classes, how many document, for example, in the news reader, what we are going to do now, we are going to split it as a sports and different categories, right? Different category of news. So that is we say it as a class. So that is you have to split it here. Okay, so after what you have to do, you have to fix the some rule. Based on that rule, you have to classify. But as a human, by fixing the rule in the random way, it is highly difficult. Moreover, if the rule is not properly planned, it will not exactly works to split the mail as spam or ham. Okay, so what you have to do during these cases, so you have to do some machine learning algorithm is going to perform on the data which is used to classify the or categorize the documents. So these are all the different kind of classifiers which is used for your classification. It's a naive-based classifier, logistic regression, support vector machine, k-nearest neighbor, and so on. These are all the some of the supervised classification, supervised classifiers. So how we are doing the text classification, how we are sets the rules based on the bias. Okay, so this is actually the words, the original data we are having. What you have to do, you have to create the bag of words. This is a kind of features which is extracted from the data. In this case, what you have to do, you have to identify how many times the data is presented. So likewise, you have to create the numerical data, guys. This is going to act as a weight while we are calculating the probability. Okay, so based on this, this is actually the features we are actually created from the bag of words. Okay, seen is 2 time and seen is a weightage of 2, sweet is weightage of 1, and whimsical it's a weightage of 1, recommended weightage of 1, happy weightage of 1, and so on. Based on this bag of words, we are going to create a class. I will show you one application and then we move on to the implementation part. Okay, this is how the, I hope so. This is actually what we are seeing in a morning session. Okay, Bayes theorem representation. This is what I said, guys. Okay, while you are doing a classification application, you want to calculate the argument max. Okay, in such a way, it should have the probability of the class given document. So which class is having a highest probability, that is actually we are going to map it as a posterior, maximum posterior probability. That's why here we are given it as a MAP. Okay, so that category, the document is actually categorized in that particular highest probability category. Okay, so this is actually the base rule. We are dropping the denominator. In the morning itself, I told, right, for the different classes, if you are doing, the denominator is actually common. Okay, yes, no, only it is getting changed, but the given data is not going to change, right? So far we are dropping the denominators. So this is for one class. Suppose if you are having a more number of features, this is actually a more number of features. How to calculate the conditional probability of the more number of features? Okay, that is we have to know. I will show you. So this is how we have to do, guys. This is what we are done in the morning. For yes condition, what is the wind? What is the outlook? What is the humidity? Okay, and then we are finally multiplied with the prior probability. Okay, likewise, this is a property of conditional probability, guys. Okay, so the x1, x2, xn given C can also be written it as px1 of C, px2 of C, px3 of C, and so on. So this is how the naive Bayes it's actually become right now. This is a posterior, this is a prior probability of the class is multiplied with the conditional probability or maximal probability, we can say. Okay, this is a multiplicative one. In the probability representation, the property of the probability representation, it simply multiplies the datas. Okay, with the more number of classes, it simply multiplies that. So x1, x2, x3 is, guys, different words. How many features you are considering for identifying the spam or ham? Okay. So this is how we have to calculate the probability for the multinomial model. Okay, this is the probability of the class. This is actually the document given class, particular document given class. Okay. So what is actually the parameter estimation, guys? Why we are introducing a parameter here? This is, we called it as a Laplace smoothing. In the morning itself, I explained, right, why we are introducing a 1 here to avoid the zero frequency problem. In some case, this particular class is actually, this particular feature is not available in your given document. During that time, what happened? It becomes zero. If the one of the element is become zero, the entire data is become zero. The entire manipulation is become zero. Am I right? Because it is a probability. The probability is in the form of multiplication. Okay, try to avoid that one. We are adding the 1. Let us say the one more example I try to explain. So this is a unigram example. This is a data we are taken. This is a weightage of the particular data. So we have to calculate whether the given sample is a positive or negative. Okay, this is how we have to calculate, guys. So this is a each and every data weightage. So if you want to calculate the total probability, simply multiply all the values. That's it. So this is how we have to calculate whether the given data is positive or negative. So for example, this is a weightage value. This is a value we have to compute from the data. Okay. So this is actually the values. So this is a data 1 and this is a data 2. Okay. Consider, guys. So I1 0.1, it's a 0.2, a 0.1, 0.001 and 0.1, 0.01. This is the data. So what you have to do, you have to compute the probability of the data. Based on that, you try to classify either it is a positive or negative. Whenever this value is greater, then the data is positive. This value is greater, the data is negative review. I hope so. While you look at this particular slide, you can easily understand how the naive Bayes works. Consider the words. These are all the bag of words. Okay, this is a class. Okay, Chinese Beijing, Chinese class C, Chinese the Shanghai class C, Chinese Macau class C, Tokyo Japan Chinese class J. So if suppose this is a test data, Chinese, Tokyo, Japan. What about the class? We have to identify. So this is the approach. What you have to do first, you have to calculate the class probability. Okay, here how many classes are there? 2 classes. So 2 prior probabilities are available. So this is a class C and this is for class J. So out of the 4 data, 3 is actually class C. So 3 by 4. Out of 4 data, only 1 J, it is 1 by 4. Similar way, you have to calculate all the conditional probabilities. Chinese given C, Tokyo given C, Japan given C. Okay, I hope so. How to calculate this particular value, you people are know by using this formula. Count of W comma C plus 1 and count of C plus norm of V. Okay, so count is already we know that in the previous slide. Actually the formula is there. You go and see the formula. Okay, kindly go through that formula and then you calculate the values. Based on that, you try to choose whether this particular data is going to be a class C or class J. So under this calculation, what happened? This particular value only it is high compared to this, right? This is a argmax. This is how we have to multiply the given features. So different features, how many features? 1, 2, 3, 4, 5 features. So 1, 2, 3, 4. So this is actually 3 times. Okay. So 1, 2, 3, 4, and this is 1. It's a 5 features totally. Okay. This is actually repeated. That's why they are raised to the powers. I hope so. Okay. This is how you have to calculate the data. This is how it calculates the, sorry, it classifies. This is, we called it as a multinomial naive Bayes classifier. I hope so you people are clear with this one. So then we have to measure the measure the performance of the classification by using a confusion matrix. Okay, it's fine. We will see the implementation right now. I hope so you people are clear. Is there any doubt regarding this? How to find the correlation for text data from the bag of words, right? So see guys, so many NLP process are there. Mostly in that one, what you have to do, so the problem arises, some of the data having a same weightage. That is actually the problem. That is actually the correlation here. Okay, what you have to do in some of the cases like that, you try to drop some values, or otherwise any one of the value is, or otherwise you have to penalize the sum of the values, depends on the weightage. Okay, that is the only way you have to do the correlation. The actual correlation is in the particular data at the same weightage. That is actually the correlation in the bag of words. I hope so you people are clear with the naive Bayes, how they are approaching the text data. Okay, we will see the code. Then you people are getting very clear with that. Sandhya?
So is my screen visible?
Yeah, just a minute. First, yeah. I
Yeah.
hope so. Screen is visible. So,
Participants, is my screen visible to all? Yeah. Okay. So we'll just start with the implementation of Bayes. So today, what are the topics that we're going to see is a lot of examples. We are just taking one of the example from what we've seen in the theoretical class. So one goes with we take the text data from different news groups. So we take the inbuilt data present in a 20 news group dataset that's there inbuilt in sklearn, and we apply different feature extraction techniques on the text data, and we giving it to a multinomial naive Bayes. So this is the first one that we would be seeing. The next one goes with a sentiment analysis using Twitter tweets. So we've collected a data set that contains the Twitter tweets, and we look at what are the different pre-processing steps that we do on the data and extract the required information to be given to the multinomial naive Bayes again. And further with that, we'll be comparing the performance with another model that's existing already there, and this particular code will implement it with grid search optimization. So this is the third example that we'll be seeing. And the next one goes with PCA. So PCA, we'll see initially we'll see a random distribution of data that is having 200 dimension, and further we apply PCA to reduce the dimension to 2, and then we plot it and we see. So this will be the first example that we see in PCA. Post that, is my screen not visible?
Sandhya, are you there?
Yeah, I'm there, sir. Is it visible now?
Yeah, fine.
So where did it stop? Yeah. Okay. Okay. So in PCA, we'll be seeing two different applications. So one involving thank you. So randomly initialized data points. We first reduce the dimensions for that. The second one goes with we take a hand-returned data sets present in sklearn, and we apply PCA to that to reduce the dimension, because we know it has a 8 cross 8 pixel image. So from 64 dimensions we'll be reducing it to 2 dimensions. So by this way we'll see how PCA is applied for image based data. Post that, we'll see something how PCA is used for noise filtering. We'll apply the same data set again and see how it's used for noise filtering, followed with eigen phases. So this is the agenda, and followed this we'll also see how naive Bayes is used for classification of a in terms of a binomial classification. That's whether we have yes or no case. So for that we'll be taking the diabetes data set. It's called the PIMA diabetic data set, which has 9 rows of data, and in that we'll be applying naive Bayes, and this particular code is completely written in Scratch for people who are interested in research. So where we calculate the probability, summarize the label, summarize the data, every step that was there in the implementation of naive Bayes is completely written from scratch. So we're just sharing this with the participants for them to have a better understanding of how internally naive Bayes happens for a huge data, right? So starting with the first one, so that goes with classification of data set. So initially we have given some explanation for that for you to recall whenever you use the notebook. So following this we initially declare some random points using the make blob function in sklearn. So this is going to give us a randomly distributed data points. So once this is done, so here we'll be seeing Gaussian naive Bayes first, and following this we'll be going for multinomial naive Bayes when we come to the text classification, because in text classification the number of classes increase, so we go for the multinomial one because of the classes. So as we all know, in Gaussian distribution the model is trying to fit our data into a Gaussian curve. So as we all know, Gaussian is a bell shaped curve that has huge amount of data onto the top part, the dome part of it. Followed with it we have lesser information towards the end, the vertices part of it. So when we are giving a data to a naive Bayes model in such a format, what the algorithm tries to do is that it tries to fit in a Gaussian curve in the distribution that it is found there, or it assumes that the data is distributed in a Gaussian manner. So looking over here, we just see circles of ellipses, but how do we get to know that a Gaussian is internally inside it? So let's have a closer examination. On a closer examination, if you can see, the center part alone is crowded with more samples than the other samples. So on this we assume, or considering this to be a dome shaped one, the center part or the top dome shape of the bell, in the bell curve, the top dome shaped part alone comes in the center of the ellipse. That's how we get the two set of data points to be fit onto the Gaussian curve. So any data distribution we have, the first thing that we do is to help fit to fit it into a Gaussian in a Gaussian model. So that's what we do. So for implementing the Gaussian neighbors, we have sklearn that has the Gaussian naive Bayes. We just simply call the model and plot the and give it the training and test samples, so which we have already declared in the make blob function. So we've just got the make block function where we are declaring two clusters, and each belonging to one class. So this is class 1 and class 0. That's given in a y, and x has the training samples. So we are now passing this to the model.fit function. The model.fit, it's very simple. So this is the standard step that we use for all the sklearn implementations, which most of you are already familiar with. So we just import and we call it and we give the fit function, right? So following this, when we give the model.fit function, the model fits the data onto the onto the hypothesis, and now the fitted hypothesis is now generated. Now what we do is next we now again generate some random blob for predicting it, and now when we are predicting it, yeah. So now when we're predicting it, we see that if you can closely examine, there's a blue color and a red color boundary drawn in between. So which indicates the decision boundary of how a Gaussian is now able to classify our data. So this is a basic example of how Gaussian works for the classification of data. So when we are applying it for other data sets, the only difference is that here instead of x and y, we'll have to put in our training and test samples. So either we one hot encode the data when we're passing it to y, and x as the training samples. So this goes with Gaussian. And now the same thing we'll see it in the tabular column based for each samples. So for each sample we see that the first sample belongs to class 1, and followed with till the second, third, fourth, fifth, and so on. So till the last second one, the sample classifies it to be in class 1. whereas the last two samples are belonging to class 2. So this is the way of how the probability we obtain when we are classifying it. So this shows how Gaussian neighbors is doing the classification with probability. Now, getting into multinomial naive Bayes. So for this, we are using 20 news groups dataset from sklearn. So this is a dataset that has textual content with regard to 20 different news categories. So atheism, graphics, Windows, hardware, Mac hardware, and so on are the different categories that are present inside the dataset, the 20 news group dataset. So in that, what we're doing for our application, we're just selecting a few categories. So we're just taking 4 of them for our analysis, and we are classifying them as train, and we are putting them as test. So, and that this is just a brief so this is just a look at how a data set looks. So one sample in a data set is like this. So what are the information it has? So as we all know, it's a news article, so it says from, and what is the subject we're having, what's the originator, the organization, distribution, and this is the short paragraph of the news that's there under this particular heading. So fact or rumor, Madeleine Murray, an atheist who eliminated the use of Bible reading and prayer in public schools. So, and it goes so on. So now our task here is to convert the given text information into a form that can be put into model.fit in our multinomial naive Bayes. So considering the text features here, now our task is to get this into a vector form or into a numerical form. Initially, there were two different, like there's a hierarchy. So first, initially we started with something called count vectorizer. So what this count vectorizer do? It is very, very simple operation. Once when we're given few sentences of data, it just counts the occurrence of number of words in the given passage. So for example, taking evil is repeated 2 times here. Taking problem is repeated 2 times here. So with just counting the number of repetitions of each word in the given data, what happens? We are generating a column of data. So for this, we use count vectorizer. Again, count vectorizer is inbuilt inside sklearn. We can just import it and give our data. And when we give fifth dot transform example, so the given data is now converted into a form that's in the form of a tabular column, something similar like a one-hot encoding. So this is a kind of pandas frame that we obtain when we are converting our text data into a columnar form. So what happens for each word, evil, horizon, problem, queen, it just shows the it just shows the occurrence of or the repetance that is there. So for example, here evil is repeated 2 times. So in let's see here, for sample 1 has evil, and sample 2 also has evil. So sample 2 also has evil here. Horizon is repeated only in the third. So horizon has the third one there, and so on. So this was initially
Sandhya,
yes, sir.
please 3 minutes more.
Yeah,
Accordingly,
sure, sir.
just tomorrow we can. Tomorrow there is 2 sessions of
Yeah,
Suresh.
sure, sir, sure.
If there is anything left over, we can make it out. Means okay. So
Yeah,
Suresh
sure,
is
sir.
there online, please.
Yes,
Yeah,
sir.
yeah, yes, sir.
Okay. If possible, we will be completing it today. If possible, otherwise we can continue tomorrow also. Tomorrow morning 2 sessions are there. In
No
that
issues,
case,
sir.
we can plan it accordingly.
Yeah, yeah, no issues, sir.
No issues. So by this way, we are able to convert our textual data into a columnar form. But what was one problem with this one was it started giving too much weight on words that were repeating but did not have much information. Let us consider we have lot of auxiliary verbs like am, is, was, were. So these are like additional auxiliary verbs that happens to repeat a lot of time in a given paragraph, but they do not carry significant information. So this kind of information that was adding on to the count vector was not required. It was kind of repetitive, and it started giving a false information to a model. So to overcome this, we came with something called TF-ID vectorizer. So TF-ID vectorizer stands for the term frequency inverse document frequency, which most of you are already familiar with. So what was the
Sandhya,
how?
tomorrow we continue the session.
Yes, I'll
So
just
that
complete with
tomorrow
this.
morning
Yeah,
Tomorrow,
I'll
itself.
complete.
if possible, tomorrow it is possible means okay. At least this part you can finish it. So multinomial you can
Yeah,
take it up tomorrow.
yeah, sure, sir, sure. So only this one I'll close with it. So the how TF-ID actually overcome the problem with count vectorizer was TF-ID, which weights the word count by a measure of how often they appear in the document. So there was a weight factor coming into it, and through this way, it was not merely the count, but there was a weight factor coming into it and gave importance to the appearance of words. So this is how TF-ID gave weight to our words. So as you can look here, it's weighted even with 0.5 and 0.6, horizon with 0.7 because it occurred only one time, and off with 0.6, and problem with 5 and 6 and 7. So this is the difference of how internally count vector operates, where we have only just a kind of one hot encoding count values going on, and the next one had weighted values with TF-ID. So once we've got the train data from the TF-ID vectorizer, we pass it to the multinomial naive Bayes, which is there in sklearn. So once when we're giving it to it, we frame the model.
Sandhya, is it possible to take it tomorrow, that part?
Yes, sir, sure.
Yeah,
Sure.
please. Participant, do you have any type of questions to be asked, please? If there is.
Guys, any queries?
So, okay. Then now, my sincere thanks to Suresh, who have been continuously taking about 3 sections in a continuous way on dimensionality reduction, decision tree, feature engineering, and respective projects on which the demo was started by Sandhya. However, the part of which is not being completed will be taken tomorrow, because they got 2 sessions on that, where Suresh and Sandhya both of them will be available. So that tomorrow morning they will be taking up basics of ensemble techniques, hyperparameter tuning, and SVM, support vector mission. So afternoon section, there will be Suresh Kumar, assistant professor from information technology of Sri Krishna College of Engineering. We'll be talking on unsupervised learning. Project will be based on IoT data analytics, where you will be taking up examples and you'll be doing some kind of a demo in the cloud. So that is the way in which we have planned for the next day section, that is on Friday session. So hope that this session have been useful for you, and you can send up your feedbacks, which is already been circulated to you all about these 3 sessions of today. Once we receive the feedback and other things over there, so tomorrow's sessions similarly we'll be going ahead with it. So on Saturday we will be having only 2 sessions, because the reason here is that there should be only, we have been planned for 15 sessions actually, but there is only a 14 session scheduled over there in the AICTE itself. So accordingly we have made changes over there. So on Saturday we will be having G. Dinesh, who is a founder of Decrew Technologies, also will be sharing some of his machine learning models and model deployment in reality, that is whichever he has done is in his company. And Sandhya will be talking about neural networks, natural language processing, and recurrent neural networks on the day with a project demo. So these are an overall glance of tomorrow and day after tomorrow's work. So with this few words, I thank very much Suresh and Sandhya being with us for a long time. Of course, Sandhya was been contributing day before yesterday itself, and Suresh is contributing a lot on this, and they have been with us in MSc Data Science, with the MSc Data Science also. So we thank you very much, Suresh. We thank you very much, Sandhya. We thank you all the participants who have been serious about it right from the morning. Nearly about 80 to 85 candidates who have been very serious and been putting a lot of questions. We thank very much every one of them for their active participants. Thank you all very much. We'll meet you tomorrow morning. Thank you.
Thank you, sir.
Thank you, sir. Thank you, guys. Thank you for